Imagine a vast, dark region of space that pulls everything toward it. Once something falls inside, it's drawn toward the center called the singularity where it gets crushed. But what if we told you that this isn't exactly how black holes work? What is the singularity, and what's really on the other side of that pitch-black abyss? Prepare to explore the mind-bending world of black holes, where reality is even stranger than fiction. Black holes are some of the most complex phenomena in space. Every aspect of them is puzzling. When a massive star, about 10 to 30 times the mass of the Sun, runs out of fuel, the balance between gravity and internal pressure collapses. The star implodes and undergoes a supernova explosion. The issue with our current understanding is that we rely on different theories to explain phenomena on various scales. Quantum field theory, for instance, is great for explaining the behavior of particles at atomic and subatomic levels. But apply this theory to galactic scales, and it becomes useless. That's where Einstein's general relativity comes in. The trouble with black holes lies in their size. They start as enormous galactic objects, but then they rapidly shrink to much smaller, sometimes even quantum-sized scales. For example, if the Sun were to become a black hole, it would need to shrink to about 1.8 to 9 kilometers in radius. Theoretically, any object can become a black hole, and there's a formula to calculate how much an object must be compressed to become one. This boundary is called the Schwarzschild radius. So, how small would Earth need to be to turn into a black hole? Picture the entire Earth compressed into a sphere just 0.35 to 0.88 centimeters in diameter. But what if an object's radius were exactly zero? Both math and physics break down in such a scenario, and this is where we encounter the singularity. But does such an extreme concept exist in reality? Let's break it down with a thought experiment. Imagine the simplest form of a black hole: small particles of matter floating in space. These particles don't exert much force on each other, but gravity starts pulling them together. Over time, the particles press closer together, their combined mass and gravity growing stronger, and the space around them begins to collapse. This forms an event horizon, a boundary that allows things to enter but not escape. This type of black hole is called a Schwarzschild black hole. It has mass, determined by how much matter went into creating it, but no electric charge or spin. Now, what happens if you cross the event horizon of such a black hole? Let's say it's large enough for you to enter with a spaceship. Once inside, you might try to escape by firing your engines. But no matter which way the ship is facing, physics says you will be inevitably drawn toward the center, the singularity. To visualize this, imagine a long, narrow hallway with an exit only at the end. Once you step in, the door closes behind you and there's no way out. The hallway has a moving walkway, like those at airports, that pushes you forward at the speed of light. No matter how hard you try to run in the opposite direction or move sideways, you'll still be pulled forward by the walkway. This is how scientists believe black holes operate. But things get more complicated when you introduce mass and rotation. When a large, rotating star collapses, the rotation is preserved, creating a spinning black hole. Quantum mechanics, which was designed to explain the strange behaviors of the microscopic world, adds more uncertainty. It suggests that fluctuations in spacetime and quantum variations play a key role in the event horizon of black holes. You've probably heard that nothing can escape a black hole, but here's where it gets tricky. Close to the event horizon, particles and antiparticles are constantly popping in and out of existence. But what if one of these particles manages to escape the black hole's pull? The late Stephen Hawking proposed a theory called Hawking radiation, which explains that when a particle-antiparticle pair forms near the event horizon, one of the particles may fall into the black hole while the other escapes. The escaping particle takes energy from the black hole, which means the black hole loses mass over time. If you give it enough time, on the order of 10 to the power of 68 to 10 to the power of 103 years, the black hole will eventually dissipate, leaving nothing behind. But if nothing remains behind, where does all the mass and energy go? In the real universe, there is no such thing as true infinity, or at least we haven't observed one yet. So, when scientists run calculations that lead to infinite values, it suggests there's a flaw in the theory. It's too simple to apply in extreme cases. Imagine plucking a guitar string at its resonant frequency. According to the simplest model of wave behavior, the vibration of the string would amplify endlessly, stretching out to infinity. But in reality, this doesn't happen. The fact that the model predicts infinity means it's incomplete. There are limits to the theory, especially at larger scales, where a more refined theory is needed to avoid infinite values. So, what does this mean for our understanding of black holes? If singularities aren't real, perhaps at the center of every black hole lies something else, something beyond our full comprehension. As always, scientists have several ideas. According to Roger Penrose's theory, singularities are an inevitable consequence of general relativity. Anything moving through space under the influence of gravity should follow a specific path known as a geodesic, the shortest, most efficient path through spacetime. Penrose proposed that the universe itself is a kind of fabric, shaped by these geodesic lines, some of which are straight and others curved. These paths are endless, much like a line drawn across a sphere. Penrose proposed that geodesics, the paths that objects follow in spacetime, should converge inside black holes, leading to a point where spacetime itself ends, creating a singularity or infinity. Stephen Hawking believed that the Big Bang began in a similar manner, as a singularity where all geodesics traced back to a single point. However, a recent paper by Roy Mungrel offers a new perspective, suggesting that rotating black holes could change everything. Instead of having a single event horizon beyond which nothing can escape, rotating black holes have two distinct horizons, an outer horizon and an inner one. These act like invisible barriers marking regions where gravity is so intense that even light cannot escape. Rotating black holes also feature an ergosphere, a region around them where spacetime is dragged along by their spin, moving faster than the speed of light. If you were near a rotating black hole, no matter how hard you tried to remain stationary, you would inevitably be caught in its rotation. These ergospheres are like whirlpools in spacetime, affecting the motion of nearby objects and producing bright light due to the extreme speeds involved. If an object manages to escape the ergosphere, it would leave with more energy than it entered with, in theory making it a nearly unlimited energy source, though extracting that energy remains an impossible task. Additionally, black holes don't just have singularities that form a point. For rotating black holes, the singularity takes on a ring-like shape due to the effects of angular momentum, which smooths it out. To visualize this, imagine a drop of paint falling onto a piece of paper. If the paper is stationary, the paint forms a single dot. But if the paper spins as the drop falls, the paint spreads out into a ring. Similarly, when matter falls into a rotating black hole, its path is not a simple circle but spirals in all directions, eventually filling out a three-dimensional shape. Instead of following a flat plane, particles around a rotating black hole move in a manner akin to a bee flying in the air, forming a donut-shaped structure in space. In these scenarios, matter doesn't fall directly to the center of the black hole. Instead, it's more like throwing a leaf into a strong wind. The wind's swirling movement carries the leaf in all directions, sometimes bringing it closer to the ground, other times lifting it up. This behavior, known as the bend around rotating black holes, means that objects don't necessarily fall into the singularity but instead might move in complex ways within the event horizon, influenced by the centrifugal forces. This phenomenon, called the ring singularity, differs from the point-like singularities of non-rotating black holes. It is a gravitational field stretched out by the object's rotation, creating a region where spacetime is warped so severely that it defies our standard understanding of physics. Imagine this as a cosmic vortex, where matter and light follow intricate paths shaped by the black hole's spin. Understanding these elements is crucial because they offer valuable insights into gravity and matter under extreme conditions. The study of rotating black holes, particularly those with angular momentum, challenges our basic theories and expands the boundaries of human knowledge. One fascinating feature of rotating black holes is their ergosphere, a region surrounding the event horizon where spacetime is dragged along with the black hole's spin. The ergosphere extends outward, creating a zone where even light is compelled to follow the rotation of the black hole. Inside the ergosphere, an object might gain energy by entering and splitting apart, with one part escaping with more energy than it originally had. This process, known as the Penrose process, offers a theoretical way of extracting energy from a black hole's rotation. The ergosphere adds complexity to how we perceive the boundary of a black hole. Unlike the event horizon, which marks a point of no return, the ergosphere allows some degree of freedom for particles and photons to move. Recent studies and simulations have also explored the possibility of observing these effects through cosmic measurements, such as detecting gravitational waves or high-energy particle emissions, which could provide direct evidence of the ergosphere and its role in the dynamics of black holes. In essence, rotating black holes present a fascinating puzzle for physicists and astronomers. They force us to reconsider our understanding of gravity, space-time, and singularities. While much remains theoretical or inferred from indirect observations, ongoing advancements in astrophysical research promise to unravel more of the mysteries surrounding these enigmatic cosmic objects. As technology improves and our observational capabilities expand, we may soon uncover even more surprises hidden in the swirling depths of black holes. Each new discovery brings us closer to understanding their full impact on the universe and our place within it.